Hi, hello. Welcome to the fifth edition of Flair's online builder workshops. And as we're slowly progressing towards more advanced themes, today we're going to see how to use FDC and really dig into the depths of what FDC is, what you can do with it, and how you can use it to pretty much empower your blockchain application to go further and to do something much more that is available on normal blockchains. And as usual, there's going to be a Q&A at the end and maybe a surprise if you're fine and if you can answer the questions that are going to be posted. This time we made it a bit more FDC oriented, but you'll see it's not that difficult. So as usual, I copied the slide from the initial presentation. So we already know why we are on blockchain. The main purpose of blockchain is this designed to be secure. So the ability to know that everything you're doing, that the whole computation, pretty much the whole system, the whole computation part, the whole consensus part, everything you're doing is secure, and security is your main focus. Apart from knowing that you can reach pretty much anyone at the other side of the world, you also have this assurance that pretty much anything you do, A, can be tampered with, and B, is going to be executed, and there's really no way for people to censor you. So those are two important things. And throughout the blockchain, the important thing is that all the computations that have happened in the past can be verified independently by just providing me with a sequence of blocks. So I can see that nobody has been cheating in the past weeks, in the past months, in the past year by just taking a sequence of blocks without any additional input. And this is important, but can also be problematic. As we've seen before with the FTSO part, you need to somehow get the data from the outside. How do you get the data from the outside? Well, here's where Flare comes in. So you can do it through multiple ways. You can ask somebody to put this data to you, you can do it yourself, or you can ask the protocol to provide the data points you can need. But as always, there are some drawbacks with each of those approaches, and you need to strike a balance between how useful you want the data to be, how soon you want the data to be available, what's the refresh rate, and what are your security assumptions. And since we started on blockchain, you know that the security is quite important. And you're on blockchain, and you know that the applications that you're doing, the funds that you're securing, and pretty much any computations you do on top of this are important and constantly under threat of attack. You must also be sure that each of the steps in this chain of trust, each of the steps in the chain when the data comes from somewhere to your application and something is executed and some payout is made, or you issue something to user, or you do anything, each of those steps have to be secured. And if possible, it has to be secured by the same amount as everything else. Otherwise, you know what your weakest link is, and that's probably when you're going to have troubles. And it's not just the security, it's also the ability to know that your data is going to be available at the time when you need it. So it's both decentralization and the ability to stop censorship. And this is where FDC comes in. So the main purpose of FDC is to provide external data points directly to chain while not compromising any of those things. So by still allowing you to interact with it, by being sure that nobody is doing anything funky with it, and by making sure that you can always access the data. And even if you use some external third-party service, even if you use, as we'll see today, a data layer from somewhere else, you can always verify that the data there is correct, and you can always run your own and be assured of that. Okay, so we've started with FTSO providing probabilistic data to chain. So FTSO allows you to gather data points and put them on chain. And those data points until now have been prices. So prices are fine and nice because you can easily order them, do consensus on them, and pick a median, pick a weighted median according to the stake weight of the data providers and say, okay, this is my correct price. This is what I'm going to use in my further calculations. But this time we're going to be talking about deterministic data. So not about something that a close nearby is fine, but something when you need a concrete response that's going to be used in a further calculation. The simplest example is a Bitcoin transaction. Let's say somebody has paid me X Bitcoin to my address, which is Y. It's important to know that the address Y has been credited with this Bitcoin. It's not fine to say, okay, address Y plus minus 1 bit at the end has been credited. That's useless to me. So I need to be sure that in this type of data points, when I access them, I get exactly the data point I need, and I'm sure that pretty much everybody else has seen the same output. So we're talking about deterministic data. And this is where Flare Data Connector comes in, because it allows you to attest through the network of validators, which are the same as data providers, that a specific data point has been seen out of chain, and this specific data point can then be used on blockchain by being sure that everybody has seen it and they're all attesting that it is the same. So you have this whole security assurance, and we had to put this on a blockchain, thus providing you with sufficient granularity of data, sufficient refresh rate, and also we had to keep in mind how to make sure that this data does not clog the blockchain and also allows the rest of the blockchain to progress properly. So there's also a question of efficiency. How do you do it efficiently, but still quick enough and still giving you access to data that is rich enough to do anything on top of this? So Flare Data Connector, what does it do? So it allows attestations about specific data points. We'll see which specific data points they are. How does it work? Well, it works through the network of attesters. And the attesters are the same as validators and the same as data providers. The whole ethos of Flare builds on top of the set of data providers, ensuring that each data point coming to chain, everything that is used in further calculations on chain is always secured by the whole stake of the network. So we want to provide security on all levels, not just on the level of block calculation, block building, and block progression, but also on a level of data acquisition, where you can be sure that the blocks that you're using are correct and the data points that those blocks are relying on are also correct. And we'll also quickly cover on the data types that we have on the network currently and what you can do with them. And an important thing is the data points, the data types that are currently on the network are, I wouldn't say limited, but they're specifically tailored A to the F asset system and B to some types we've discovered that are useful during the development phase. But you, the whole community, can always propose new data types, and those new data types are easy to add. Pretty much the only thing you need to do to add new data types is to firstly propose it, get the data providers to come to an agreement that they will support it, provide them some additional incentive, and then at the end the data providers will vote, add the data type, and anyone can use it. So the governance initially provided some data types, but later pretty much anyone can add data types through so-called community incentives in the same way as an FTSO. So Flare works as an infrastructure layer. So we're providing you all the necessary protocols with initial points you can use, and additional things can be added at a later point by users. Okay, so FDC, let's see how it works. So FTSO works as an oracle. Data providers are constantly pushing data on Flare, and when the data is on Flare, you can read it through smart contracts. With FDC, we had to go a bit differently. With FDC, you have to be active and start and work through a few steps. So the first thing you do as a user is observe some external data. And let's just provide a nice example in the beginning. So let's say I want to set a specific Ethereum transaction when somebody has donated something to me, or a transaction when I've seen some coins move, or maybe a transaction where I've seen that there's a huge discrepancy in the Uniswap price. So I start with an Ethereum transaction that I wish to transfer all the information about it to Flare. So that's the first step. I see information, I see some data point that I want to use later. I then prepare this information, I then prepare a request that will be issued to all data providers through Flare to request an attestation about this thing. So now I have the information. I have to prepare it in such a way that the FDC protocol will be able to consume it and provide some response to it. The easiest way to do this is through the verifier server, and we'll be doing this today pretty much throughout this workshop, and see how it works, what the response is, what is the result that you get, and how you can use it, and also how you can understand it yourself. Once you have this request prepared, which is pretty much just a set of hexadecimal characters, an encoding of a specific data type, this is where the chain part starts. So now we have in hand an Ethereum transaction prepared in such a way that the FDC can start working on it. Now you have to submit an attestation request to the FDC protocol. This is a simple call to the FDC hub on a network, which emits an event. And this event contains pretty much just the information in this prepared request returned by verifier server. And this event is called by the data providers pretty much whenever their nodes are. And now they're going to start working on it. And the data providers now go through the process of bit vote to achieve consensus on which of the data requests they should consider and confirm in this round. Importantly, we batch all the requests into one batch, that is all the requests that have arrived in the each 90 seconds through each of the voting epoch. By batching this, we achieve a much, much higher throughput while still not harming the functionality. So data providers batch the requests together. They vote through a bit vote on which data points, which data requests can be confirmed by them, because you also include some sort of a checksum, so-called MIC, the message integrity code. They vote on this, and at the end, a subset of the requests that a majority of the data providers can submit is selected. A Merkle tree is built out of them, and this Merkle tree computes a Merkle root of this Merkle tree, and then this Merkle root is deposited on-chain. So this is the work of data providers. The only thing you have to do is submit this request. Once you submit the request, they get to work. You then have to wait for the round to finish, for everything to finalize, and now what you have on-chain is the Merkle root attesting to all the requests made in the previous round. The main question that usually arises here is, why do we only consider the Merkle root? Why are we not depositing everything on chain? Well, the important thing is that the data points you are requiring, the data points you are requesting might be big, and you only want to use them on demand. So firstly, to make things a bit more efficient, and secondly, to not impose a huge burden on the validator network, thus increasing the load, thus increasing the requirements for all the validators to run them, we only require them to deposit a Merkle root, and then on demand, when you want to use this data point, you provide the whole data point that you're going to be using anyway, which is much more efficient than reading it from chain, together with a small piece of information, the Merkle proof, which is usually just a few bytes. And these few additional bytes, so usually a list of 5 or 6 bytes 32, allows you to check that your data point that you're providing is exactly the one that has been confirmed by the data providers in the round. So together all this, after the round finalizes, you would turn to another service also provided by us, the DA layer, which pretty much selects your data point. So you provide it with the data points that you wanted to prove in the beginning, computes the whole information about this data, everything you can see, together with this proof that proves that it has been proven in a specific round. And once you have the proof, the last and the final thing you need to do is to use this in a contract. And the contract is very simple. We'll see it today, and we'll see what each specific line of code does. And the contract, the only thing it does, it has to check that the proof provided alongside this data you want to use is indeed the testing that this has been proven by the FDC. And all this is just a simple checking of a Merkle proof, which is a few kchecks, and you're over. And this is nicely encapsulated throughout the library, so you don't really need to do much of it. The only thing you need to do is you need to check one of those initially deployed Flare contracts, put the proof and data in there, and you'll get an immediate response if things are correct. Okay, so that's the whole workflow of these things. It might sound scary at the beginning, but it's actually very, very easy to use and very nice to use it. So you start with observing the data, you gather the request, you submit the attestation request to the FDC protocol, you wait for the data to finish, you wait for the FDC to finish this data proof, and then after this is done, you query the DA layer to get the proof together with the data, and then you can use it. And in contract, it's a simple two-step process. You check that the thing works you check that the thing is correct via the proof. And secondly, you check that this data is the thing you want. So in our case, we'll be attesting to some transaction on an external Ethereum network. We'll just check that the events emitted in this transaction are correct. Okay, Let's see what you can really do with this. So we have a bunch of supported types, and those are currently valid supported types. So like I said in the slides a few slides ago, anybody can add a new type by pretty much proposing it to the data providers, but currently we have a preset set of types which are pretty much tailored both to F assets and to some additional general use cases across the blockchain. The one that's going to be used in this workshop is the EVM transaction, when you can attest to a transaction that's happening on another EVM network with pretty much all the additional data. So we're going to be attesting to a transaction together with attestation to a specific event happening, and we're going to be decoding this event and using it later. And then we have a few other attestations. The next one is payment. Payment allows you to prove that a specific payment has happened on another blockchain. Just to give you some clarity, so EVM transaction currently works on Ethereum, Songbird, and Flare. So those are the networks we've connected, but we're constantly working on connecting other networks, while all the other transactions are specifically tailored for other non-EVM networks. Specifically, we currently support Bitcoin and Dogecoin as an example of UTXO networks, and XRP Ledger pretty much to connect it to the F asset. So with payment, you can attest to a payment with a specific value between specific addresses on XRP Ledger, Bitcoin, and Dogecoin. And you get payment plus full information about this payment and everything that's happening around it. So who has paid, when did it happen, how much confirmation it has, and so on. You then have another more computationally intensive attestation, which is address validity. It is not really a look on another blockchain or a look on an external data point. It's an offloading of some expensive computation to some other computer. Why is that useful? Well, at some point, you want to know if you're doing payments on other chains and attesting to them with Flare, if this address on another chain is valid and can be used to transact to. And checking this in Solidity on blockchain is expensive. So what you can do, you can offload a bunch of computations to this data type, pretty much request the FDC data providers to verify that this address is valid, give you some response, how this is valid, what type of address is it, standard hash, and so on, compute this off-chain, get this data on-chain, and then act on top of it. Then there are three more specific data types, but still useful. So there's confirmed block height exists, which is very useful if you want to observe what's happening on other chains, specifically if you want to see if they're properly progressing. So let's say you want to execute a payment on XRP Ledger, and you want to know if the XRP Ledger is properly progressing. With this data type, you can pretty much say to data providers, please attest that A, XRP Ledger has at least X blocks, and B, can you compute to me how much was the block production rate in the last few seconds, minutes, hours, and so on. So in this way, you can easily observe what's happening on another chain, what's happening with regards to the liveness of other chains on Flare. What that means is that even the problematic cases when you want to redeem something somewhere else are nicely handled because you can always know what's happening there. And the second two, balance decreasing transaction and reference payment non-existence, are useful when you want to know that something on other chain has happened in a way that you hadn't predicted or hasn't happened. So balance decreasing transaction allows you to pretty much single out a transaction and check if a specific address in this transaction has had a balance decrease. So you can see if a specific huge Bitcoin transaction has decreased a balance of some address without ever knowing what the initial balance was. So it's pretty much a police operation when you can see that somebody should be holding something, and you can always observe that at the end of this transaction, the balance at the end was smaller, even though the outputs and inputs can be mind-boggling web of some old outputs and whatnot. And the reference payment non-existence is pretty much a jewel of the payment, where you can say, please prove to me that in the last X blocks, last X minutes, a payment with a specific reference has not been observed on a network. Why is that useful? Well, you might require somebody to pay you something, and instead of them having to provide the proof of payment, you want to also be securing yourself by you allowing to provide a proof of non-payment directly to the network. And again, this is executed by a set of data providers. So all these things are the things that you can't really do on blockchain, but you want to know and you want to use the information about them later. And how do you do this? Well, easy. You return to the previous graph and you see how you can firstly observe the data point in some off-chain instance that you want to use. You prepare the data, you submit a request. Once the data providers prove it, you pretty much just get the proof and use it later in your contract, in whatever capacity, knowing that the whole set of data providers has seen this thing happen, has confirmed it correctly, and then you can use it on a network by being assured that the whole set of validators, pretty much the whole stake of the network, has voted that yes, we've seen this in exactly this capacity. Okay, so let's jump right in. We're gonna take a look in more detail at the EVM transaction. Why EVM transaction? Because EVM transactions are really, really nice. You can see a lot of information about them, and importantly, you can see what events they've been emitting. So what that means is I can take an EVM transaction, transferring some ERC20 tokens, and without going into the details what's happening there, I can just listen to events, and if I know that the events are well behaving, as they usually are with ERC20 tokens, I can do a bunch of stuff with them, pretty much move that information to Flare and use it. And yeah, and that's pretty much enough of that by PowerPoint to everyone now. And let's get our hands dirty and see what we can do with it. Okay, so we're gonna start, as we usually can, by pretty much going to Sepolia. And let's just select a random transaction and see what's happening there. Okay, let's select the latest block. Let's get a transaction. And this one, there's a transfer method in it. And it should have some, nope, no events. Bridge asset. Okay, bridge asset has a bunch of logs. That one looks good. And it has a transfer event, which is really nice to decode in our example. Okay, so we have this transaction. And then now the next thing that we want to do is see how the verifier server prepares this. So what we're going to do is we're going to take the transaction hash and go to the verifier server, which allows us to prepare the transaction. How do you get the verifier server? Well, we have all this available directly in the Flare Hardhat periphery Hardhat starter package, which if you wanna go through this workshop at a later point, you can pretty much download and follow us, because I'm going to be following one of the example codes in there. So we're operating on Sepolia, which is a testnet. So we're going to take a testnet verifier, open it. Just a second. I'm gonna open, let's just open a verifier. Just need to put it there. Let's start with the XRP verifier. That is going to be the easiest one to check. So XRP verifier, let's just see how the XRP verifier works, and then we'll check the verifier for the EVM transactions at a later point. Okay, so the easiest thing to do is this prepare request. So prepare request, pretty much what you have to do is you have to provide an attestation type, which is this attestation type, source ID. So what we're doing, we're requesting a transaction, source ID, we're requesting this from test XRP, and the request body, which pretty much says, okay, please attest to me on this transaction. Important thing, the verifiers are guarded by the API key, which is just zeros for test networks, and it allows you to pretty much play with verifier around without having to use your own infrastructure. This is good because you can pretty much go around it. You can play around with it, and you're just going to be rate limited if you do this a bit too often. So we're going to authorize ourselves. Authorize, we're going to close it, and then we're going to try it out. Immediately when I try it out in Swagger, I'm going to get an error because I'm not using the correct source ID. So we are quite strict with changing between test networks and real networks, which you want to do if you want to have a strict separation and not make any problems or not make any errors in the real implementation. So you have this attestation type, and the source ID has to be test XRP. And if we execute this now, I'm going to get invalid because this should be sharing this. So I just changed let me just refresh this. So the only thing I did is I firstly authorized myself by copying these zeros. Authorize myself. And then I wanted to pretty much prepare a request for XRP transaction. I executed this and I got this error that I've got the wrong source ID. So like I said before, so the source ID has to be test XRP, just so that we make sure that you never mix testing networks and real networks. And if I execute this now, I got an error that this is an invalid request. Why is it an invalid request? Well, because you can't see this request anywhere, because transaction like this doesn't exist on XRP ledger. We're just going to put zeros here, and we're going to go to testnet scan XRP, pick a random block and a random transaction in it, and see what's happening. Okay, so let's pick that one. We have one payment. That should work. And we get this. So we get a valid transaction response and an ABI encoded request. What's this? This is the thing that we're going to send to the FDC to prepare everything for this transaction. And if you take a closer look at this ABI encoded request, it's pretty much the attestation type, the source ID, and if you take a look at this 1657, this is exactly the 1657. This is exactly the hash of the transaction we're using. The rest are some canonical data points, those 0 and 0 encoded as 0 hex bytes. And in the middle here is the MIC, message integrity check, that allows the FDC to properly assess which data we're getting back. And all this, you might be already familiar with this. This is just hex encoded payment and test XRP, which is in the same ethos as we had hex encoded payments in the hex encoded things in the FTSO. Okay, so that's for XRP. For the EVM transaction, we're going to get a bit different data points back, and the easiest way to see this is to check the spec, which is just which is much easier to decipher, and it's available pretty much on the it's available on GitHub, and you can easily see it. So let's check the EVM. It's important to not know this by hand and to pretty much check them on the fly, because you can get much more thing out of it. So for EVM, you need to provide a transaction hash as before. So we're going to be providing a transaction hash, a required confirmation. So on EVM, you can be much more stringent on how much confirmations you want. So for Ethereum, if you want to know that the transaction is fully finalized, you want to wait until proper amount of slots has been filled out, so you know that the beacon chain has indeed finalized these things. Or you can be a bit more on a dangerous side and pretty much say, okay, I'm fine with just a single transaction being through. And then the most important thing for EVM is this. So you can say that I want to list this set of events. So I want to list all the events provided in the transaction, and I want to use these events in my later point. And you can then select some indices that you might want to list, and you can select up to 50. Okay. And this is the request. So this is what you're requesting the transaction to do. So this is what you want the transaction to give you. This is what you want the FDC to prove. But in the response, you get much more. So you get all this metadata about transaction, So what was the block number, the timestamp, source address, was this a deployment, the receiving address of the transaction, value, input, status, blah, 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 blah. But importantly, for events, and this is what we're going to be using today, you get a list of events, and each event has all the necessary data that you need to process each event independently. So for each event, you get all the event information that you can use and decode it. So if we take a look at this Sepolia transaction again, let's see how the logs look in the Explorer. You'll see that pretty much what we have mimics the things that you get for the logs inside the Explorer itself, the things that you want to know about the event itself. So you get log index, where exactly this was found in a block. You get the emitter address, which means that you know which contract has emitted this event. So you know that something was confirmed, something was emitted by USDT. And you get a list of topics. Why are topics important? Well, topics are the things that are indexed in the event. And by getting the topics, you can see and you can know what the event is about. Importantly, this is not strictly in specification, but this is how Solidity works. The first topic is in Solidity, importantly, is the keychack of the event signature. Why is that important? This way you can identify the event that has happened, so you can pull the event information out and use it later in a contract. And then you have data. So this is this additional data, which is nicely decoded inside the Explorer, but not necessarily. And then you have another Boolean flag, which is if this event was removed. But in our case, we pretty much care about those three things. So if we're going to be taking a look at this specific Ethereum transaction of Sepolia, what we're going to do, we're going to take this transaction and we're going to be checking for all the events emitted from this address. We're going to single out the transfer address, and then we're going to check from who to whom how much value was transferred. And all this gets encoded into FDC data point, gets pushed to the FDC to verify. This gets added to the Merkle tree. The Merkle root gets computed. The Merkle root is put on chain. And once the Merkle root is put on chain, we can use the DA layer, so the data availability layer, to get the proof together with the full information, pretty much a huge JSON that we'll see today, or a huge Solidity struct that you're going to use on contract. And then once this is on contract, you can do anything you want. Okay, so enough blabble. Let's see how the code actually looks. So if you go to this Flare Hardhead starter, today we're going to be looking at the FDC example, which is a script going through all of this. I have some things already filled in, but we're going to fill them in together. And we're going to be looking at this Ethereum payment collector, which is a very, very simple contract, which only does one thing. It allows you to collect transfer events. What does it do? Well, if you provide me with this EVM transaction proof, the data type of this EVM transaction, I'm going to loop through all the events, check if the emitter was correct, and if the emitter was correct, I'm going to save this to this struct token transfers. And then at any later point, you can use these token transfers. I've missed an important thing. Before doing anything, what you need to check is you need to check that this transaction is valid. So let's see how the data types in Solidity actually look. Okay, so all these data types are already included inside the library provided by this Hardhead starter, which is pretty much the periphery library. So you should be using this. But let's take a look at this proof exactly. So the proof, the proof that you get, the thing that DA layer gets you, is composed of two things: the Merkle proof, the thing that gets verified, and the response. And the response is pretty much just a Solidity struct that contains all the information we've seen here. So it's a Solidity struct containing all this information. So it has some metadata when the thing has happened, the request body, which contains information what we really requested, and the response body, which is all the initial metadata plus events. And the only thing we're going to be looping over are those events, which are nicely encoded in Solidity, so you don't need to do any of the additional verification, any of the additional parsing, the only thing we need to do is to parse the data according to the topic. Let's see how that looks. So we have a contract which we want to collect transfer events happening on another chain, happening on Sepolia. So what does this contract do? If somebody provides me with the proof that can be used through FDC, firstly, I check it with the FDC if the thing is correct. And this is very easy. So the only thing you need to do is get through the contract registry library, get the FDC verification, which is the FDC verification contract deployed on Flare, which does all this necessary checking. So it gets the full transaction information, checks the round, gets the Merkle root that is currently deployed on chain, gets the Merkle proof that you're providing it together with the data point, computes the hash, and returns either true or false, depending on if the hashes match or not. And that's it. That's the FDC part of the logic. So the only thing you have to do is call the library, and you're done with it. You now know that the data point you have on the chain is correct. Now it's your business logic. So the only thing you need to do in our case is to go through events and make sure that the events match and the events are whatever you need them to be. So we go through all the events, we get the current event, and the first thing we do is we disregard the events that are not from our contract. In this case, we had the USDC contract, but since we're going to be observing a different contract, I'm just going to copy this thing and say, nope. Let's say this is the contract we're going to be checking. So for each event, we check that A, it's emitted by the correct contract, and B, we check that this is indeed a transfer event. So like I said, if we have some topics, and if the topics at index 0 is not the signature of the transfer event, we're going to revert. Otherwise, we now know that this specific event has been emitted by the contract we're observing, and we want to get out the sender, which is an address, the receiver, which is an address, and we just unpack the value. How do we know how to unpack this value? Well, we just unpack the uint256, which is directly encoded into the signature of the event. And that's it. So on the Solidity side, this is pretty straightforward. Everything you need to know from the FDC part is included in the library, and the rest is a business logic. Importantly, no matter what kind of data you get here, even if someone were to provide you with the faulty data, this thing would revert if the FDC has not come to the conclusion about this specific thing. Okay, so we have the contract. Now let's go through this part. So we now have the contract. We know what the application logic is. We've observed the data. Now we have to go to verifier server, prepare a request, submit this to the FDC, and pull it through the DA layer. Okay, let's do this. And to do this, we pretty much follow each step independently. Okay, we're gonna take the transaction we're observing. So this is our transaction ID. I'm gonna change it here, and I'm just gonna slowly go through the code and explain what it does. So you've probably seen this function to hex before. So pretty much it encodes everything to hex, which is very useful for this tutorial, but in real use case, you would pretty much use a function from the Flare provided library. But you can see here it's not that big of a deal. So it's pretty much encoding and padding to 0. We import the necessary stuff. We're going to be working on constant 2. We get our transaction ID, and we're going to be preparing the request. The prepared request, as seen before with XRP, is nothing really that problematic. So it's just a huge string of hex data that encodes all the information about our request. And the only thing we need to do, we need to call the verifier for ETH, get the EVM transaction, and we need to provide him with the information on which network we're doing this and which data type we want. So let's just see what exactly we get as a response. So I'm going to run this. It has to recompile, and that's what we get. So the prepared request, again, those are just encoded hex types. This is the MIC, and if you look carefully, you can see that our data, our transaction that we're looking at, is nicely encoded here. Okay, and now for the more important part, how do you submit this? We firstly have to deploy the contract. Why deploy the contract? Because the next stage that we need to do is request this attestation from the FDC. But how do we request it? Well, we need to know where this FDC contract is alive on Flare. You can directly copy the FDC address, which is a good idea, but not really good idea because the contract can change. The best way is to use the contract registry library, which allows you to always have the correct information about contracts on Flare, because we're curating it and the governance is making sure that it always points to the latest contract no matter what. So I've pretty much upgraded my payment collector with two additional helpful functions. The one just returns the FDC hub from the contract registry, and another one returns the fee configuration, which you can use in a more advanced mode to provide specific fees for the FDC request so you don't overpay them. But we're going to disregard this for this time. Okay. So what I'm going to do, I'm just going to firstly deploy this payment collector so that we can work through the contract and don't have to worry about the addresses. So I'm going to deploy the payment contract. Okay, so it's deployed at this address. I'm just going to change the address here. And what you should always do is you should always make sure that you verify the contract pretty much immediately after the deployment. Why is that good? Well, that is important and nice because you can then always check what the contract is doing, and it's easier to debug it through Explorer if you need. It's easier to interact with it, and so on. Okay, so we got the contract, we got it deployed, and now the next thing is pretty much to submit a request, and we'll see what exactly this does. So the request is pretty simple. So here we've prepared the request with all the necessary information for the request body, and we've made the request to the verifier server and got back this JSON, which is somewhat readable, but you don't want to work with it or do it manually. And to submit this to chain, pretty much the only thing that you need to do is get this request data in your hand, and then use the FDC hub by calling the function request attestation. And this request attestation pretty much pushes this information, pushes this encoded request to chain, adds some value to pay for the necessary fees, and that's it. And then we wait for the round to complete. Let's firstly execute this, and then we'll see what's happening, and we can observe the FDC round happening real time. Okay, so the request is prepared. Now we're preparing the attestation, and we can check the progress in two ways. So I'm just going to copy the transaction hash, and this is the transaction round. So first thing that we're going to take a look at is this transaction hash. So this is the transaction from my address to FDC hub, and it has emitted this method call. So FDC hub emitted an event attestation request with some bytes, which is exactly the bytes that we've requested for the FDC to prove, and some value, the fee, so the data providers can know what kind of fee they're getting if they confirm this. So this has been put out. People are now listening, data providers are listening, and now we can observe what's happening here. So here I've immediately calculated on which, at which round this has been requested. So we can already observe what's happening with it. It's going to refresh the page. Let me check. Went to cost on 2. This has been, so that's, oh yeah, that's 1 to 8. Okay, so that's my transaction. I was just a bit slow and didn't calculate everything correctly. And this is my transaction, and all the data providers have submitted it and are pretty much happy with it. So you can see that they've pretty much voted yes on it. And if I click on a specific transaction, I can see it's exactly the one I've used. So AE295F. Let's check. AE295F. Yeah, so that's exactly the transaction I've requested. And it has now been A, requested through the FDC, and B, all of them have voted that they're going to approve it. And now the only thing that we need to do, since this is confirmed, we have to go to the DA layer and get proof of it back. And the DA layer is pretty much a service that lives on Flare servers. You can use it. It's rate limited if you want to do something heavy duty with it. But for a nice thing that we're going to do today is is all right. So we copy the round, and we're going to take a look at FDC. FDC, try it out. We're going to check our voting round ID, and we get back this response. So what we get back in the response is exactly is a list of those proofs here. So, and since our round has only had one attestation, one request, we only get one proof back. So we get a list with exactly one thing. So we get a response, attestation type, source ID, lowest used, some metadata, the request body, so what we requested, together with the response, which is a huge JSON. Let's increase this by a bit, which is a huge JSON with all the necessary information about our transaction. So the block number, the timestamp, the source address, and most importantly, directly the events that are in. And if we take a closer look, we're looking at two events emitted by the ADBF. You can see that that's the first event. The second event is emitted by 5E2, which is that one with a much larger data point. And you can see that this is encoded as a much larger bytes. And then another event emitted by AF with 3 topics and so on. So we get all this in response, and the proof is empty. The proof is empty because we are in a very specific situation when there's only one thing here. So there's only one leaf in a Merkle root. So exactly the hash of this leaf is exactly the Merkle root. And that's easy to check, but the proof is empty, and thankfully we don't have to do anything with it because this already gets handled by this contract register. Okay, so the only thing that we need to do now is to get this proof together with the data point and push it on chain to our contract, and the contract will pretty much just verify it against the FDC, make sure that this is correct, and it's gonna make sure that all these events are properly filtered, save the events that are interesting to us, and push them on chain. That's the only thing. So just put it there. Let's go back to the script. Now we can go away from the submit request, and we can go directly to prepare request. So I'm just gonna change the round. So an important thing is knowing how do you calculate a round. The round is relatively easy to calculate. I've hard-coded some numbers here, but it's very easy to get those directly from the Flare metadata registry for contracts. It's pretty much every round, every voting epoch lasts 90 seconds, and you have a starting timestamp, and the current round is just the block timestamp minus starting timestamp divided by the length of the epoch. Okay, so we get target round ID, and the rest is very simple. So we request the proof, which is just a call to a different URL than the one we were looking at, and then we just await the proof and data JSON, which is just going to get this back. And to submit this to chain, we pretty much just request a proof. You get the proof. We initialize our contract at an address that's already deployed at, and we submit this transaction, wait for it to finish, and we're done. Let me just see if I have to do anything. No. Okay, so let's just run this part. So you see that the rest of the code is simple. The most involved part is knowing where to put each of these. So starting with getting the data, preparing the request, submitting it, and now after all this is done, you pretty much just get the proof and initiate any action you have on your contract. So we're gonna run this again. We get the request because we need it for the proof. We get the whole proof, which is a bit larger, and then we submit it. Okay, let's see how this went. So if I go to my transfer event listener, and if I go to custom explorer, if I check my contract, you can see that it was deployed 10 minutes ago, and half a minute ago, I had this collect transfer events. Let's check the transaction itself. So it submitted a huge amount of data. So all the data we had to be submitted. And this is all cold data, remember. So this is still much, much cheaper than having all this on-chain. I've submitted this, the contract has checked it. And now if I go directly to the contract, I can see that if I call this read method, that is gonna return all this, that's gonna return everything that has been saved in the token transfers. I can just call it get token transfers. I can see that there's exactly one thing in, which is our transfer from this transaction. And I can easily resubmit this, and I'll get another transfer in, another one. Okay, so that's an important thing to notice. Once the thing is on chain, okay, so now I've got two because I've added it 2 times. Once the thing is on chain, you can always reuse it. And that's an important piece of the efficiency we've directly embedded into the system. So data points are stored not as a whole data points, but data points are only stored as Merkle roots for a specific round. And when you want to use the data points, you provide the whole data point together with the proof that this was included in specific round, and you only pay for data at that point. So this allows us to have a blockchain that is very scalable, that doesn't impose any additional requirements to validators, while still allowing you to gather much, much more rich information than just knowing what's happening on your chain, and doing this quickly and without any fears that the gas transaction fees are gonna pretty much eat your wallet away. This is the main part of the FDC. So you want to make sure that the things are efficient as possible, but you also have all the necessary data richness. Okay, so that's pretty much it. Once again, all this code, everything that we've gone through today is available on Flared Hardhat Starter. We're currently upgrading the Foundry package to pretty much include the same code, just with all the necessary Foundry libraries that will allow you to easier interact more easily with all these necessary verifier servers, data availability layer, and so on. So you have all these functions already pre-written, so you don't have to care about how to encode stuff, how to pad it, and so on. And I would encourage you to start here, play around with it, pick your favorite network, pick your favorite transaction, and see which events you can get out of this. And yeah, play around, and if you need anything, we'll be available. Okay, so here's some space for a Q&A. And in the meantime, check this code, check this QR code, and see if you can gather some more information and learn something new. Okay, so, and now for Q&A, do we have any questions corresponding to the topics of today's session? Let me just check. Okay, so we had a question from somebody: how do I get emails days before sessions are happening? Well, we usually send the emails just a day before, and you can register on the Flare webpage. We're gonna try and push this email maybe a bit further away, just to make sure that you're getting all the necessary information beforehand. There's a question: if XRP is going to go up, how do you need to learn this shit? Is there any other classes to help a beginner? Well, there's a bunch of different tutorials, a bunch of different resources you can use to start developing on blockchain. We're currently in the midst of a education package with Encode, so it might be worth checking those tutorials, where pretty much one of our DevRels, Anthony, is going through the whole process of how to start on blockchain, what blockchain is, what you can do, what you can start with, what are the tips on the way, and so on. I would encourage you to also check our developer page, when you can find some nice use cases. Although if you're not that familiar with Solidity, I would firstly start with pretty much Solidity tutorials on the web, which are quite abundant. There's always a question with should you be going with Hardhat or with Foundry? Foundry is getting quite a lot of traction in recent times, so I would suggest starting with this. Although I still find Hardhat a bit easier if you want to go through all these interactions with web, and if you want to do some difficult data manipulations. Then it's okay, what's the best way to start learning this? So if you're, like I said before, if you're totally new to Solidity and blockchain development, I would really recommend this Encode education program that we have. If you're totally new to FDC, we got quite a lot of documentation about FDC and how data can be moved between different blockchains and what are the pitfalls of doing this and how you can learn this. If you want to learn more about cryptography, I would pretty much recommend you to start on any of the additional resources. I found Stack Overflow to be very helpful when you have questions, but the beginning I would recommend some sort of online courses on this. But yeah, but if you like this part, we're going to be releasing much more information about how specifically to use FDC. There's going to be a whole blog post series. There's going to be all this necessary starter code. So I would go with this. I got another question somewhere else, which is, you said that new chains can be added later. What do you mean by that? Well, FDC is connected to multiple other chains. So currently we support Bitcoin, Dogecoin, XRP Ledger, and 3 EVM chains, so Flare, Songbird, and Ethereum, which are directly connectable. Adding additional blockchains on top of this it depends on how you want to add a chain. So EVM chains are relatively easy to add because they can easily be integrated into the EVM transaction type. Other chains are a bit more difficult because for the attestation types to really provide you with the full assurance that something has happened, you need to make sure that the underlying chain is fully integrated and that the data providers are correctly querying everything related to this. So for payment, if there is a specific way of paying something on the underlying chain in a very specific transaction, or I don't know, paying it in an internal transaction, we need to always make sure that the FDC can see this. So that means that some chains are quite difficult to integrate. The easiest way to do it is to add a new attestation on top of existing chain, which allows you to see a bit more without really jeopardizing the existing chains and without really having to do much more additional coding. One thing to know is that we're constantly adding these new types pretty much by design. So one of the important new types that is going to be added pretty much in the next month is going to be so-called Web2 type, which will allow you to query an arbitrary Web2 resource and process it in Solidity. What this will allow you is you would take a specific web page, provide some additional data, some post-processing data, and you would be able to pretty much say, okay, is the Twitter API reporting this thing? The whole set of data providers will check the Twitter API, and then you'll get a response. Yes, the Twitter API is responding with this JSON, the sum of all the numbers is 10, and you could interpret this as, yes, this tweet has achieved 10 retweets in the last 20 seconds, or so on. And all this by a network of independent decentralized verifiers, put it on chain, and pretty much the opportunities are endless. I think that's all for the questions. You're more than welcome to join the next session when we're going to dive deep into how to create your own things, how to extend all this. And if you've been following our socials, I would like to invite you to the big hackathon that we're doing together with Google Cloud, when you'll be learning and you'll be working on the top tier technology currently, when you can add even more things to FDC, even more things to Flare as a network, when you can pretty much put your own code and say, please run this for me, get this, run this for me, execute it, make sure that this is attested to a set of trusted execution environments, and then you'll get this on chain and you can proceed from there. So the main idea is that we're constantly evolving the network to get more and more information on it and to allow you to build more. Okay, that's it. Thank you everyone for joining, and we'll see you next time.